couple model for differential privacy, which is used in practice in a lot of places, done like theoretical foundations for it in the rather influential paper. And I'm a little bit biased towards it, but he's also done a lot of nice work in statistical estimation of privacy. But without further ado, he's going to tell us about some theoretical, underpinnings of membership inference attacks. So, without further ado, John.
Yeah, that one's pretty great too. Hey, thank you. It was a very lovely introduction. And I have to say, it's my first time visiting Waterloo, and everyone's been very kind, and I've really appreciated how many people have taken the time to meet with me. It's a very nice place to visit. Although a downside of that is I think I'm starting to lose my voice. So your job as the audience is to ask a lot of questions, so I get a chance to not talk for a bit. If they're the rambling, more of a comment than a question type, where you just want to hear yourself talk for 2 minutes, like even better. Right. So here I'm going to talk about some very recent work with Adam Smith and Mari Haifam, who is my postdoc, and it's about basically sort of a learning theoretic view on privacy attacks. So in particular, I'm going to tell you about sort of a class of privacy attacks called membership inference attacks. And I'm going to tell you about sort of a question of how can an attacker learn to do a membership inference attack? So we're going to sort of take the view of the attacker and try to understand what they need to produce a membership inference attack. And so I'm going to spend, in the talk, I'll give sort of a very quick overview of like what the work is about. And then I'll spend a good chunk of time, I think, sort of trying to kind of explicate the process of coming up with like a meaningful, I hope, tractable, seems to be theoretical question, and sort of figuring out what the result should be. And then I will, give a little bit of hints at sort of what the technical ingredients are. So hopefully, even if, sort of our theorem isn't the thing you remember from the talk, you sort of learn a little bit about this very cool problem of membership inference in the privacy space. Okay, we're off to a great start with the clicker. Sorry, I'm trying to make it so it clicks. Good. So, all right. So
can you click OK on the thing to get that out of the way?
Dude, it's really hard to figure out where the mouse is. Good.
Thank you.
Okay, now I'll hide that over there. Okay, so this is a talk about sort of privacy in machine learning and statistics. And to sort of set the stage, I think there's sort of an interesting intuition that a lot of people start with, which is that privacy kind of shouldn't be a problem in learning and statistics. And the reason for that is in sort of a learning problem, we have some distribution or population that we want to learn about. And we draw some training data or samples, and we think of that as what we're going to use to learn about the population. But we're also worried, of course, these are real people with real data, and we might be concerned about revealing their data. But the good thing is we don't really want to learn about them anyway. What we want to do is we want to use their data as a proxy for releasing some demographics or training some predictive model that is sort of relevant for the population. So it feels like if we've done our job very well and we've come up with the ideal learning algorithm, the only thing the output should really depend on is the population. The samples should actually be sort of immaterial. So that sounds great. It sort of feels like when we're doing learning and statistics, we should kind of have privacy for free because ideally we're not even using the samples at all in some sense. But of course,
click again, I guess.
Yeah. Of course, real learning algorithms have to use their samples. That's how they learn. And what we know after, at this point, maybe 2 decades of research is that they inherently have to reveal a lot of information about their sample. So not just information about the population, but specific information about the people in the sample. So like something that they learn about you because you are one of the sampled people, not something they learn about you just because you're a member of the population. And there's lots of different threat models, both in theory and in practice, that we've used to kind of sort of ratify this informal statement I'm making. There's sort of very influential reconstruction attacks from Dinor and Nissim in 2003. More recently in LLMs, we've seen lots of work on extracting sort of whole pieces of training data. There's sort of related work showing that learning algorithms in some cases have to kind of memorize their training data. But for today, the sort of threat model that I want to think about is what's called membership inference attacks. This is something that goes back to very long ago in 2008 by academic standards in an influential work by Homer et al. And membership inference is sort of one way of sort of witnessing a failure of privacy. It's sort of one way in which a training algorithm or a statistical estimator can reveal information about its sample. So here's sort of a very high-level description of what a membership inference attack is. So we have some population or distribution, which is this cloud over here. And we're going to do a thought experiment where we draw like some data set from that population, let's say IID. And we imagine there's some targeted person. So this is like you in the data set, and you're kind of worried about what the algorithm reveals about you. And we'll think about also some sort of counterfactual where you are in fact not in the data set, you're just some independent random member of the population. We'll run the algorithm on one of these two data sets to get some information about the population. And then there's some attacker who's looking at this output and actually knows your data and is just trying to figure out whether you are in or out. So they're basically just trying to figure out if you are a person in the data set or some random member of the same population who's independent of the data set. And so they look at these two things and they say in or out. So the goal is we have an attacker who observes the output of the algorithm and tries to infer whether some person, hypothetically you, are in or out of the data set. So this was first introduced in practice as a way of attacking genomic data sets in this Homer et al. Paper that was very influential. It had some influence on kind of the policy around these genomic data sets. We were sort of doing some theoretical work on this a while ago in 2015, where we demonstrated that this type of privacy compromise is actually inherent in a lot of situations. It's not just a result of a particular algorithm. And I'll say a little bit more about what we actually showed in that work when I start developing what we do. And then this really took off around like 2016, 17, when this influential work of Chokri et al. Demonstrated that you could carry out these membership inference attacks in sort of big black box neural networks in practice. So not just as kind of a theoretical model or something that works in these kind of small data sets. And of course, a valid question is like, why does anyone care, right? Like, why would it be a problem if an attacker who already knows your data finds out that you're in the data set or out of the data set? And the answer is that often like membership in the data set is already kind of the stigmatizing thing. So in this example of genomic data sets, there were really like two data sets, and there was a set of people who were known to be in one of the two data sets. So it was sort of known who participated in the study, but it wasn't known who was in the control group and who actually had some, stigmatizing medical condition. And so testing membership in the data set, like your data was out there. The only thing the attacker didn't know was whether you were in data set 1 of control people or data set 2 of non-control people. So membership was kind of the only like privacy compromise you could imagine. And so obviously this at least in principle can be highly sensitive. So people have studied membership inference attacks in a variety of different contexts in privacy. So they're used sort of in roughly two different ways, and then in a continuum between them. So one of them is as a way of proving sort of lower bounds on the error you need to achieve some strong privacy notion like differential privacy, which you don't need to actually know about for this talk. So in some of my work in my thesis with Ban and Vedant, we used this as a method. We basically showed that these membership inference attacks have to happen unless you add a lot of noise to the data. And this is a way of saying that any private algorithm needs to add a lot of noise. But in this setting, right, we basically get to make the attacker as sort of adversarial as we want. We can kind of assume they know basically everything except for just this last bit of in or out, because we just want to prove like a worst case lower bound. And so when you view these things as real attacks, they start to look not very compelling. They start to look fairly contrived. On the other end, people also think of this as a real threat against real systems. And there, of course, you care a lot about what you're assuming about the attacker. So, what actually is the population you're assuming? What training algorithms are you using? What knowledge does the attacker have? What capabilities do they have? You want, ideally, the attacker to be as weak as possible to make the attack most convincing. And And this is sort of more the view taken in work on kind of privacy auditing and sort of using these attacks to empirically evaluate privacy. And of course, there's like some spectrum between these things. So when I say that there's kind of more and less realistic attackers, like what do I mean? Like what are some of the things that make an attacker more or less realistic? So there's lots of questions you have to fill in this picture. So one is like, what kinds of data distributions am I talking about? Did I make them up to make the attack work, or are they a broad class of naturally occurring distributions? Another question is like, what does the attacker have to know about the distribution? So like maybe it's a nice distribution, but the attacker doesn't know which one. Maybe they know the distribution exactly. Another question is like, what type of sort of training algorithm am I using? Is this an attack that's specific to one algorithm or like a generic attack? And similarly, like, what does the attacker need to know? And you could go on and on with sort of different questions about what would make a membership inference attack kind of convincing, either in theory or practice. And for today, I'm going to focus on just one of these, which is what does the attacker need to know about the distribution? So, there's a range of like ways people have thought about this in the literature. Like, does the attacker need to know everything about the distribution, but just not know about the data set itself? Or can the attacker, only know some very broad thing, like the distribution is, IID with like some, reasonable properties or something, right? So like, do they really need to fit to the distribution well? And we're going to study this question using sort of sample complexity or kind of statistical learning theory. So what we're going to do is we're going to model the attacker as not knowing the distribution, but having access to an independent set of samples from the distribution. And this is how like all kind of practical attacks work. So pretty much every paper you would open up on membership inference attacks will either explicitly or sort of implicitly represent the attacker's knowledge of the distribution through either they're like explicitly through their ability to have samples from the distribution, or from sort of their ability to kind of produce outputs from the same distribution as the real output, but independent, which they can clearly do if they have enough samples from the distribution. So yeah.
What if there is a correlation between the data point?
What if there's a correlation between the data points? So
they are not ID from the...
Right, so modeling membership inference when there's a correlation between the data points can be a little bit tricky. And so for today, we're going to look at kind of the standard theoretical model where the data points in the data set are IID, and then the auxiliary sample is more IID samples. But you're right that we could imagine that these are sort of jointly distributed, and then we could ask reasonably, like, what should the auxiliary sample be like in that case? So it's a good question, but we're actually going to just punt on it for today. Okay, so let me give just like the little preview of like what the result is. So what we're going to show is that there are kind of simple, reasonable settings, at least I think so, in which any membership inference attack requires the attacker to have a very large auxiliary sample. So I'll of course quantify this and I'll formulate an actual theorem for what this means. But let me give kind of like a basic idea of what I mean by large and why I think it's like qualitatively large, not just like some number. So first of all, we're going to look at a setting of like mean estimation. So you have data, which is a bunch of D, every data point is like a D-dimensional vector. And D is really big. It's more than N. So this is like sort of the over-parameterized regime in learning. And what we're going to show is that the attacker needs a lot more than N auxiliary samples. So why is that an interesting kind of threshold? Why is more than N important? Well, N is the number of samples that the honest algorithm had to produce the output in the first place. And often in the real world, we think of samples as kind of a limited resource. So we kind of think that the algorithm making the output has collected sort of as much data as they can about the problem. And if I'm now asking the attacker to collect dramatically more data, there may be some settings where that's not reasonable. So there certainly may be settings where it is, but if you think about something like training LLMs, which is not directly what the work is, like getting a big enough sample is like an enormous challenge. So asking someone to have like asymptotically more data to run the attack is just completely unreasonable. Another reason why this is sort of an interesting threshold is that pretty much all the practical attacks I know have a very particular way of using the auxiliary samples, which is that they just train their own sort of model as a reference. And so they all can be implemented using the same number of samples n that was used to train the real model, and they don't really benefit from having more samples. So one interpretation of our result is we say that the kind of methodology people use in practice is, at least in principle, not optimal. Like they're using sort of a restricted class of attacks that can't capture sort of all of the optimal attacks. So I don't know yet how to like improve real attacks in real settings, but at least it seems possible that you can. And we'll get to a future work where you can bet that'll be on. Okay, so that's kind of the like high level pitch. So let me outline the rest of the talk. So I'm going to give you a little background on membership inference attacks and just kind of tell you like what I think sort of the basic theory you need to know is to kind of appreciate the result, and also what I just think everyone should just know for like just to be a basic educated member of civic society, what you should know about membership inference. I'll talk about what we know about like sample-based attacks. So this is sort of a new model, but it was kind of something that work in hindsight was addressing. And so I can sort of interpret some older results as being some partial progress on the question. I'll tell you just what our main result is, and I'll give you some sketch of the proof, which involves some useful kind of general things about how you prove lower bounds for hypothesis testing. All right. Any questions before I go on? I know that was fairly high level, but please do ask me questions when we get into the more kind of technical parts. Okay, so let me just describe like the basic sort of threat model that we're going to be looking at. Let me just like quickly formalize like what a membership inference attack is. And I'm going to formalize like a super basic version of it. So this is not the only thing you could want. It's kind of the minimal thing you would call a membership inference attack. And since we're proving lower bounds, that's kind of good for us. So we're going to assume to start there's some known population P. I think at some point maybe I switch between P and D because sometimes I talk to statisticians and sometimes I talk to computer scientists and they don't agree on the right letter for a distribution. There's data that's drawn from P. And what is this data? So there's like the training data, which is x1 through xn. That's the data that I'm actually going to use to run my algorithm. And then there's x0, which is going to be like the target person that I'll think about in a thought experiment. This is like another person who's not in the data set. I'm going to train some model, like I'm going to run some algorithm M on x1 through xn, and I'm going to train some model, and I'll call it mu hat. And then I give like the target to the attacker. And there's two cases. There's the case where I give the target x0 to the attacker. So the attacker is looking at a person who is not in the data set. They're an independent member of the population that's not in the data set. And there's the orange case where I give the attacker x1. And like x1 is just sort of a convention. So we're going to be looking at a very symmetric setting where if I'm going to give a person a random member of the data set, it might as well be the first person in the data set. The attacker gets T, so they get the data of the target, and they get mu hat, which is the model. And their job is just to return like one bit, which to help you remember, I'm calling in and out, but occasionally I think it'll end up being 1 and 0. So here's a little picture of Snidely Whiplash doing that. And like, what's their goal? So their goal is just to simply distinguish between these two distributions that I defined. So, in one case, they see, oh, I'm sorry, I have my A's and my M's. No, sorry, I have this right. A is the attacker, sorry. So in one case, they get a target who's in the data set and they get the model. And I want them to say in, and I want them to do that 2/3 of the time. Just like I want them to do that better than random guessing. And in the other case, they get the model trained on x1 through xn, and they get x0. So in this case, he's supposed to say out, but the probability he says in should be less than 1/3. Again, it's a pretty weak definition of membership inference because, in practice, I would like him to have much higher confidence. I also might be worried about things like maybe he can identify x11 in the data set, but not a random member of the data set. I'm not doing any of that. This is just a very simple model where he's either looking at the first element of the data set or he's looking at x0. And I'm sweeping some assumptions under the rug, but just to make it simpler, I'm kind of assuming that the algorithm is sort of symmetric so that there's no loss of generality having it be like x1. But if you don't like that, just think of x1 as like a random person in the data set. Okay, so we're going to be talking a lot about this model and various tweaks on it. So if there are any questions, this is a good time to ask. And either way, I'm gonna just pause for a second to stop talking.
What do you think of mu being?
Good, so we'll get to a concrete instantiation. Having it be mu prefaces the fact that it's gonna be an approximation of the mean of this data. But in principle, like this threat model makes sense if mu is like a neural network or a regression, or like in principle at this level, it can be anything. Yeah.
You haven't yet introduced a case where they have some supplementary data yet, right?
Nope, not yet. So for now, I'm just assuming the population is known, and I'm going to tell you what we can say in that case where the attacker just knows the population.
Oh, I see, they know the population.
Yeah, so I probably should have emphasized that one.
Yeah.
Okay, so the first thing I want to tell you about is that membership inference is basically a hypothesis testing problem. So the way I've set up the problem, there are two distributions that the attacker could be looking at that are like joint distributions over the target's data and the model. So in the out case, they're looking at like x0 and the model trained on x1 through xn. And in the in case, they're looking at x1 and the model trained on x1 through xn. And I can say something even a little more, which is that these two distributions have like the same marginals, but in the blue case, they're independent. And in the orange case, they're correlated. So maybe that gives some intuition for why I can distinguish these. But at this level, the only thing that's important is that what the attacker gets as input is drawn from one of two distributions, and they're trying to decide which. So there's a really cool thing you should know, even if you've never had any interest and never will have any interest in membership inference attacks, called the Neyman-Pearson lemma. This is like one of these things I can't believe computer scientists don't just know more. So what does it say? It says, pick any two distributions, H0 and H1, and you're some tester who's trying to distinguish these things. So you get a sample Z that comes from one of these two things. How can you distinguish them? The Neyman-Pearson lemma says that the optimal thing to do is to look at the probability Z came from H1, divide it by the probability Z came from H0, and apply some threshold. And it's often written as applying a threshold to the log, but log is monotone, so it's the same thing, applying it to the ratio. And then, you pick some threshold and you just say 1 if it's above the threshold and 0 if it's below. And when I say this is optimal, I don't mean optimal in like the usual TCS sense of optimal. What I mean is like this test, it weakly dominates any other test. So if you pick a given threshold, this test has some false positive rate, and it will have some true positive rate that is at least as large as any other test with the same false positive rate. So this is like the exact thing you should do, like in an exact sense. So what this means is that in this case, where the attacker knows the P and knows the mechanism M, membership inference is sort of in principle a solved problem. Because if I know P and I know M, then at least in principle, I know exactly what these two distributions are, and I just need to compute this likelihood ratio. Now, I say in principle because, of course, if P is the distribution of a giant machine learning benchmark data set, and M is the mechanism that runs stochastic gradient descent with a bunch of hyperparameters on some neural network. Of course, you can't like tractably compute these, but at least in principle, this is exactly what you should be doing, and you should be trying to sort of do something as close to this as you can. So let's look at a special case of membership inference involving Gaussian mean estimation. This is going to be like what we do for the rest of the talk. So now I'm going to get more concrete. I'm going to say the distribution is some multivariate normal in D dimensions with some mu and some covariance sigma, which is like known to us. And I'm also going to make the model just be like the sample mean. So this is a nice case where figuring out this likelihood ratio test is tractable, like the distribution has a nice density, the training algorithm is fairly simple. Elena, were you about to ask something?
Yeah, is this Neyman-Pearson lemma, how does it compare with maximum likelihood?
I mean, it's like if you set the threshold to 0, then this is saying output the distribution with the higher likelihood. So it is maximum likelihood estimation. Of course, you often want to vary the threshold because maybe you care more about a false positive than a false. Anyway, it's basically maximum likelihood estimation for this very, very special case. Okay, so if you believe me, for this specific case, these distributions are jointly normal. They're now like jointly normal in 2D dimensions. And we can write down exactly what the log likelihood ratio is. And it's this. It is, you take the target, you subtract the true mean, and you rescale by the true covariance to the -1/2. This is like a whitening step that makes this thing a standard normal. And you do the same on the other side. So like you take mu hat, you subtract off the true mean, and you rescale to make this thing like a standard, some scalar of a standard normal. And you take the inner product between those two, and you apply some threshold. And sort of why is this a good thing to do? Well, basically what's going on is in the out case, these two things are independent. So the inner product and mean 0. So the inner product is mean 0. In the in case, they're slightly correlated, and the inner product picks that up. So what can you show about this? You can show that in this very, very specialized setting, the membership inference attack will succeed, sort of if and only if the dimension of the data is a bit bigger than the size of the data set. So you kind of just need about n dimensions in order to get enough signal for this to work. And I won't do the exact calculations, but I'll just wave my hands a little bit and say, more or less, the way you analyze this is by saying, you look at this test statistic, like you look at the red quantity, and it's basically normal-ish in high dimensions, everything becomes normal. And when you're in the out case, it's sort of mean 0 and has variance about d over n. In the in case, it still has variance d over n, but it also has mean d over n. So this thing is like a number that is distributed either from a 0 mean Gaussian or a slightly non-zero mean Gaussian. And basically the distance from 0 mean is enough to distinguish when d is bigger than n. So I'm not claiming that you should be able to follow like everything I just said perfectly, but the gist is basically that as you take d bigger, the two distributions get further apart and you can distinguish them. So all right, this is a setting where we know everything, but it's a very, very specific setting in many ways. In particular, we assume the attacker knows p, and we also assume that the algorithm is like exactly the sample mean. So let's do something a little bit more interesting. Let's consider the case where the algorithm is actually trying to do something to prevent membership inference. So it's not just releasing the sample mean, but it's adding some kind of noise. And I'm not going to be too specific about how it adds noise. I'm just going to assume that what it returns is something that is close to the true mean. When I say close to the true mean, I basically, what I want to say is that sort of every coordinate is off by about rho. So if I measure the error in L2 squared distance, it's about rho squared d. But think of rho as like some parameter for how close I am to the true mean. And also think of rho as something kind of bigger than the sampling error. So I'm adding an amount of noise that's like more than the noise that's just kind of inherently in the sample. So I'm changing just the thing that's in red. That's going to be like my convention. We're going to see a lot of slides where I change like one or two things, and the thing that changes is red. So now I want a membership inference attack that works for like all mechanisms that satisfy my accuracy bound. I don't just want to work for that one thing. So in this setting, like Neyman-Pearson doesn't apply because now the in and out distributions actually come from some family. Like every m in the family leads to a different in and out distribution with a different likelihood ratio. But I can at least still like compute the Neyman-Pearson test for Gaussians. Like the test I came up with doesn't like actually need the likelihood. It's just some function of the target and the model. So I can still compute it. And what we proved, at least sort of, okay, what we didn't exactly prove, but what I can sort of reinterpret this way with the benefit of 10 years of hindsight in this paper with Dwork, Steinke, Smith, and Vedant from 2015, is that if you use the Neyman-Pearson test, even if the test is not proven to be optimal by the Neyman-Pearson lemma, like you just use the test and hope for the best, it will be a good membership inference attack when the dimension is big enough. But the dimension has to grow bigger to accommodate the noise. And that's sort of obvious in some sense. I mean, if the noise is so big, if the noise is like incredibly big, my algorithm could just ignore the data or juice. So it's clear that it's the scale. So how big? So I need the dimension to be bigger than n. That's what I needed even with no noise. And then this extra thing, n squared rho squared, which I'm going to think of as being like much bigger than n. Like that's sort of how big the dimension needs to be to do membership inference. And it's a very realistic setting. Like it's very realistic to have a setting where the dimension of the data is bigger than the number of samples I have. Now, like, you can just believe me that this is sort of the optimal threshold, that like I can't do membership inference if the dimension is smaller, but it has sort of a special meaning. The specific bound is kind of special. One reason it's special is that if the dimension is smaller than this, then the algorithm I'm using might have this strong property called differential privacy, which will prevent membership inference and lots of other attacks. So the reason this is sort of the optimal dimension for membership inference is because, for all I know, like the algorithm really has provable privacy guarantees if the dimension is smaller. And what we show is basically like, if the dimension is sort of any bigger than that would allow, you'll get a membership inference attack. I swear we're coming to sample complexity. So hopefully what you remember from this is we can look at membership inference in this sort of simplified Gaussian setting. We can look at the noisy case where you're using like a mechanism to try to get privacy that adds some noise to the empirical mean. And even if you don't know exactly what the mechanism is, we have this nice attack that works well sort of in any case where membership inference is possible. But it assumes you know the distribution. And now we're going to talk about what happens if you don't know the distribution. Yeah.
Good. So one thing about the Gaussian, I didn't get why you even need that fancy this name and Pearson lemma. If I,
You don't.
like in the previous one, like as Elena said, you can just look at the maximum likelihood. Those two disturb. Isn't there a closed form formula for the maximum likelihood of the difference already when that's something from Gaussians?
Yeah, I mean, it's the thing in like yes, like once you realize that you're distinguishing two Gaussians, like this is the closed form for the likelihood ratio, the log likelihood ratio.
Do you think this? So I guess I don't know what this lemma is doing. Do I agree that the optimal test is to look at the maximum likelihood estimator or not? Or was it the wrong?
I mean, I agree with that because that's what the name and Pearson, like I could have said, you know, here's a fact you should know by the name and Pearson lemma. What you should look at is the maximum likelihood estimator. Like,
not maximum. Maximum likelihood estimator has some definition.
well, okay, I mean, it's applying some threshold, but the thing you're looking at is the ratio of the two likelihoods. So when that ratio is bigger than, when the log of that ratio is bigger than 0, that means H1 is the maximum likelihood. And when it's smaller than 0, that means H0 is the maximum likelihood. So it's not quite the maximum likelihood estimator in the sense that maybe my threshold is not 0, but it's more or less the, I mean, I guess sort of in practice, 0 is a pretty good threshold. Or at least a decent threshold. Yeah.
Do you have like a qualitative intuition for like kind of why D has to be sufficiently large for membership inference attacks to work?
Well, so there's sort of two. So one way of thinking about it in the noiseless case is that you know, you're more or less encoding sort of n bits of information. So you can sort of formalize the idea that, you know, if you have a data set of n out people and n in people, a membership inference attack can encode, does a pretty good job of encoding, you know, who are the out people and who are the in people. So it should sort of require like n-ish bits of information to do that, which means, okay, the mean is continuously valued, but if you sort of think of each coordinate as like a constant number of bits of information, you kind of need n of them. The intuition for the noisy case is a little trickier, which is that there's just a specific algorithm that satisfies this accuracy bound and satisfies differential privacy, provided that D is smaller than this thing. And so if one of your algorithms in your class could be differentially private, there's no hope of getting a membership inference attack against all algorithms in your class. But that's like an intuition for you. And you know, that would have to sort of do a different talk to explain what that means for other people. But you know, more or less the gist is that like there is a lower bound that says there is a way to achieve this accuracy bound that will provably prevent any membership inference. Like it will just be buried who is in the data set and who is not. You look like you don't like that statement.
No. But
Great.
for the previous question, I want to ask if we can go back one slide. I want to ask how it's on the slide very concisely. The very bottom sentence, where does that come from? that a corollary of Neyman Pearson?
No, it's just you can analyze this. So, okay, it's not exactly normal, but basically this is like in the out case, for example, this will be distributed exactly as like n0 identity. And in the in case, this will be distributed exactly as normal 0, comma 1 over n identity.
Perfect.
And so if you take the inner product between those two things, it's not exactly Gaussian, but it's a sum of lots of independent terms, so it's Gaussian-ish. And its mean and variance are exactly this.
I wanted to say that the bottom one is the distribution of H out, just the distribution of H out itself.
They don't type check, right? Because H out is a distribution over 2D things, and this is a univariate. Yeah. So I have to admit, I like this as a shorthand because it's really easy to write the mean and variance in a compact form. If it's not Gaussian, you just have to write the mean is and the variance is. So I have a sort of a weird motivation for assuming things are Gaussian, which is that it makes the slide more compact. Okay. Good. Okay, so let's talk about like sample-based attacks so I can tell you what our actual, like start to get at like what our actual result is. So now let's change the picture and we have an unknown population. So what do I mean by an unknown population? I mean like it comes from some class. So for example, the attacker knows it's a Gaussian in D dimensions, but they don't know which one. And now I want my attack to work for like all distributions in the class, not literally all distributions, but everything in the class. But I'm going to give the attacker extra information in the form of these M independent samples from the distribution. So now their view is like the independent samples, the target, and the model. So now they get like this little kind of cloud represented by some people, and the target and the model. Okay, but other than that, everything's the same. Okay, so we're just replacing one known distribution with a class of distributions and some sample access to that class. So like, what do we need? So now, not only does the Neyman-Pearson lemma not apply, or like maximum likelihood estimation isn't known to be the right algorithm, but you just can't even like compute this. Like you just don't know what this is and you don't know what this is. So it's like not just that you don't know it's optimal, it's like you don't even know what you're supposed to compute. Okay, but there's like an obvious thing you could try to do, right? So you could try to like use your sample just as an estimator of mu and sigma. So that's kind of the natural thing to do, just like estimate mu, plug it in here, estimate sigma, plug it in here. And what we can basically show is that this works when the number of samples you have is bigger than D. So why does it work when the number of samples you have is bigger than D? Well, you need to basically estimate this, covariance matrix. And you can show that as long as you get a good estimation in like spectral norm, this will be close enough to the optimal test for us to get a theorem. But if you have a D-dimensional thing and you want to estimate its covariance in spectral norm, you need D samples. Like if you have less than D samples, there's like at least one direction where you just haven't seen anything about it. So you just can't even hope to get any kind of reasonable approximation. Or at least in the worst case, you can't hope to get a reasonable approximation. Now, so what does it mean to have M greater than D samples? Well, we said the interesting regime for membership inference is when D is like n squared rho squared, which can be much bigger than n. So this says you might need much more than n samples to implement a membership inference attack. So in particular, you might even be in a setting where the honest algorithm doesn't have enough data to compute the covariance, and yet your attack somehow needs to come up with enough data to compute the covariance. And I come from like a crypto background, so the idea that the attacker is more powerful than the algorithm is something we should think about. I'm not claiming it's totally like worth dismissing, but certainly in a lot of learning settings, like the people training the models really have like as much data as like anyone on the planet can assemble, and we can't really assume that the attacker has a lot more. Okay, so this is kind of like the problem we want to understand. Like, why does the obvious membership inference attack for unknown distributions need more samples than n? Okay, so okay, good. So what do we know about this problem? Like, what do we know you can do other than this? Like, do we know anything better than this? So one setting that, again, in hindsight, you studied is what if the covariance is known? So what if you just don't know the mean, but you do know the covariance? And so if you know it, it's sort of without loss of generality for it to be the identity. So in this setting, we can sort of look at this paper from 2015, where we also looked at the setting where you have access to samples. And what it says is that you can get a good membership inference attack, provided that the dimension satisfies the condition we already had, and also that the number of auxiliary samples is at least the minimum of n and 1 over rho squared. So in the regime where you have very noisy statistics and a big dimension, you actually might even only need like a constant number of samples. Okay, and in this work, like we do show that's necessary, but it's kind of not the main point I want to. But the point I do want to make is that this is like always O of n. So in the known covariance case, the sample issue is kind of not a big problem. Like you sort of always can get away with at least a reasonable number of samples. Okay, so yeah, let me tell you sort of why I think this O of n is kind of an important threshold. Like I started to hint at this, but let me give a little bit of a sense of why this is like important. So I'll take a quick detour into like what people do with sample-based MIA in practice. So in practice, what they use is like a very restricted form of test statistic. So what they do is you compute some test statistic just looking at the model and the target. So something kind of distribution independent, like the model's loss on the target, the model's confidence on the target, some other things. But it's always like something that is not dependent on the distribution. And that gives you a number. But then you want to know if that number is kind of suggestive of someone in or out of the data set. And so you need to kind of calibrate the test by choosing the right threshold. And they kind of only use the distribution in this limited way to like calibrate what the threshold should be for the test. So that's a restricted form of test. Like it's not all tests. And in fact, it's not like what the Neyman Pearson test would do. The Neyman Pearson test, this actual statistic depends on the distribution. But if you do have a test of this form, then you can sort of always do this calibration step with O of n samples, because basically the intuition is you only need to train a constant number of your own independent models. And if the honest algorithm trained a model with n samples, and I need to train like 5 independent models, I can do it with 5 n samples. And in particular, if I have like much more than n samples, I can't like do anything with it in this form. Like it doesn't help. Okay, so we know that sort of the tests they're using at least kind of don't look optimal. Like they're not the Neyman Pearson style test, but we don't actually know that they're not optimal. Like maybe there's some other test that's close to optimal that just has this form. Okay, and so what we want to know is sort of, are there settings where you need much more than n samples and you really need kind of distribution dependent test statistics? Okay, oh, sorry, there was like one other little animated guy here. I don't know what that was for. Okay, good. Now for like 15 minutes away, I can state the results. It's like, mostly kind of a tour of like how we figured out what we thought the results should be. That was a lot of the project. So, okay, so what are the questions we want to know? We look at this mean estimation of Gaussian data. It's like a very, very special theoretical model of membership inference. We're looking at this noisy case, and we want to know basically like, is the sample complexity ever asymptotically bigger than n? I already spoiled the surprise. We showed that it can be. So what's our main theorem? Our main theorem says, and at least in the sort of easiest case to look at, let's look at the regime where membership inference would be possible if the attacker knew the distribution. So let's kind of only look at the case where d is bigger than this threshold of n plus n squared rho squared. If d is smaller than that, then it doesn't matter, because even an attacker who knew the distribution perfectly couldn't do membership inference. So who cares? But if we're in the setting where an informed attacker could do membership inference, how many samples do they need? And what we show is they need at least d samples. They need at least n plus n squared rho squared samples. And in the noisy case, where rho is not too small, this is asymptotically bigger than n. Like it can be as large as n squared samples. Okay. Okay, so in particular, this is sort of tight when you're kind of right at this threshold, because at this threshold, we said that you can always do membership inference with order d samples, just by estimating the covariance using the sample covariance. And so when you're kind of in this regime, the number of samples we show you need is like omega d, and so it's tight. An interesting technical question is sort of what happens when you have kind of more dimensions than you need for membership inference, but that's maybe a secondary thing. And to prove the lower bound, we actually just look at one specific estimator. So we want a membership inference attack that works for all estimators. But the estimator we look at is a very particular one. And it's one that's sort of very like natural if you're used to thinking about differential privacy. It's the estimator that just computes the empirical mean and then adds Gaussian noise with covariance in like the shape of the real covariance. So it's a little weird because it has to be like an estimator that knows the covariance. But in an important sense, like this is sort of what a lot of the best differentially private algorithms are trying to do. They're sort of trying to add noise from this distribution. So it's at least a reasonable like thing to look at. And if nothing else, it is in this class of estimators. So it's a valid thing to prove a lower bound. Okay, and as I said, we get sort of a consequence from this that says, if you want to do this kind of membership inference, then not only can you not just use the name and Pearson test, or sorry, not only do like simple practical things not work, but like any kind of distribution independent test. So anything that has kind of the form of a distribution independent test statistic can't work. Or conversely, like sort of your test statistic somehow has to try to estimate sigma. And since we know that practical tests kind of aren't really doing that, it suggests that there's like an opportunity to improve what people are doing in practice. So with my last, I don't know, 10-ish minutes, let me give you some like proof overview. I'm not going to get super technical, but I want to sort of walk you through like how you come up with the hard distribution. So like how you kind of come up with the lower bound instance, because I feel like it has some mathematical structure that's probably like just good to know. So what do we want to do? Like we want to come up with some hard distribution D over covariance matrices. Okay, so I'll assume the mean is 0 because we know that estimating the mean is kind of not the bottleneck here. So we'll just make it 0. But I need to come up with sort of a hard distribution over the true covariance. And then I'm going to like make my population normal 0 sigma. I'm going to make my model be like the empirical mean of the data plus this type of normal noise. And then I'll generate the auxiliary samples. So let's consider like what is hard about this problem. So one kind of naive thing the attacker could do is they could just pretend that the covariance is the identity, and then they can like just run the optimal test, which in this special case is just the inner product between the target and the model. Sorry, this should not be X bar, it should be mu hat. Okay, so that's like a thing they can always do. So when does it work? So what you can show is that the variance of this statistic is always the trace of sigma squared over n for both the in and the out cases. I'm lying a teensy bit, but like this is, right up to some little low order term. Okay, so maybe at this moment it's not quite clear what this means, but this is the trace of sigma squared over n is some variance. Now, as I said, like in the out case, this is the inner product of two independent 0 mean things, so its mean is 0. But in the in case, these two things are correlated. And so their mean becomes the trace of sigma divided by n. Right? This is just a calculation you can do if it's not like immediate. I mean, it wasn't immediate to me. It's immediate to me because it's on the slide. But like, I'm just asking you to take my word for it. So when does the test work? Well, these are kind of Gaussian-ish quantities. So the test will work when the gap in the means is bigger than the standard deviation, or when the squared gap between the means is bigger than the variance. So what does that condition mean? It means that if you do some algebra, it means that the square of the trace of sigma has to be bigger than the trace of sigma squared. Sorry, it has to divided by the trace of sigma squared has to be bigger than n. So like the square of the trace of sigma should be much bigger than n. So just to give you an example, if sigma is the identity, then the trace of sigma is d, and so this is d squared. And this is the identity, so this is d. So this ratio becomes d, and we say that the test works exactly when d is bigger than n. Good. So what are these expressions? So the trace is the L1 norm of the singular values, or the eigenvalues. So if you write out the vector of eigenvalues, of like variances, singular values, then the thing on top is the squared L1 norm, and the thing on the bottom is the squared L2 norm. I think I got that right. So when is like the 1 norm over the 2 norm big? It's sort of big when your vector is very spread out. So you have kind of even variance in every direction. And this ratio is 1 when you have like one huge direction of variance. So what does that say? It says kind of when does the test fail? It fails when the sigma you choose is like ill-conditioned. Okay, good. But this is just one test where I'm not even using the auxiliary samples. I'm just like assuming the covariance is the identity. But it suggests what the attacker should be trying to do. They should be trying to use the samples to learn the covariance so that they can make the covariance nicely conditioned. They can apply some rescaling to make it nicely conditioned. So let's consider like a slightly more clever attacker. They take their auxiliary samples and they compute some matrix H that's supposed to kind of approximate sigma inverse. And they try kind of hitting on the left and the right with H to the -1/2 to try to kind of shift everything to be more spherical. So now, I mean, this is the same like test, but instead of sigma, it's H inverse sigma is like, it's the same thing I would do if I had data from H inverse sigma and then didn't try to apply H. So when does this work? It works if like the trace squared of H inverse sigma over the trace of H inverse sigma all squared is big. So now I get sort of new eigenvalues of these matrices. And it works exactly when the eigenvalues of like this matrix are nicely spread out, but not when the eigenvalues of this matrix are badly ill-conditioned. Okay, so this is sort of a form of test the attacker is going to try to use. They might try something totally different, but this is kind of the logical thing to do. So how would I get a hard distribution? Like what I want to come up with is like some hard distribution such that it's very difficult to learn some matrix H such that H inverse sigma is well conditioned. So like intuitively, what's going on? Sigma has a bunch of directions, like it has a bunch of eigenvectors. So it's, the data has sort of a bunch of independent directions. I don't know what they are. And I'm trying to come up with a matrix that kind of scales all those directions to be unit length. And so it kind of feels like I have to know something about all those directions, right? And it feels like the hard case for this problem would be if sort of every direction could be a really big or a really small direction. And the only way to know is to like see kind of all of the directions. It's my vague intuition. So what's the hard distribution we're going to come up with? It's the following. This is like a bunch of notation for something I think fairly intuitive. So we're going to have a family of covariance matrices where it's like the identity in d dimensions. So the variance is like 1 in every direction. But then it's some big thing sigma squared in like k random directions. So mathematically what that means is my covariance will be like identity plus sigma squared UU transpose, where U is just some orthonormal matrix whose columns are like the directions of big variance. So I'm going to sort of talk a lot about like the directions of big variance and how they're random. And then like the distribution one choose is just induced by choosing U randomly. So it's like a distribution over this family. And sigma squared is just some parameter I'll set behind the scenes and won't talk about, but it'll just be something I set to be really big. Okay, so the intuition is like H has kind of, or sorry, sigma has like k big directions. And the only way to make H inverse sigma well conditioned is to have H sort of shrink all of those big directions. But to do that, I need to find all the big directions. And the intuition is that every time I get a sample, like my auxiliary samples will kind of span an m-dimensional subspace. And so if m is not as big as k, there's a bunch of big directions that I just have kind of no information about. I can sort of intuitively choose them like kind of after I've seen the auxiliary sample, and there's kind of no way H could like guess what they are. It's a very loose thing. It's not exactly what's going on, but it's like the right intuition. So I don't really have time to go into like much of the proof. The proof is sort of an analysis of the following slightly complicated distributions. So in the out case, what I do is I like see the auxiliary samples x0 mu hat, where like all of these are sort of based on the distribution sigma that's chosen randomly. So they're all kind of correlated by the random choice of sigma. And in the in case, I get a slightly different version of that distribution, where now they're like correlated both by the choice of sigma, but also by the fact that x1 and mu hat are also a little correlated. So we sort of tackle this in kind of two steps. I don't think I really have time to kind of tease apart these steps, but the first step is kind of a nice reduction to the case where you get 0 auxiliary samples. So what we do is we basically say, look, there's k big directions. You get m auxiliary samples. I'll just imagine that those give away m of the big directions for free, and the other k minus m are uniformly random, and you get no samples about them. And so we can show that that intuition basically holds, and that up to some error, it's enough to just analyze the case where you get no auxiliary samples, but with different parameters, slightly different. Okay. Then the rest of it is basically a lot of working with slightly messy distributions. Once you have this distribution, you get something that is basically characterized by, like, there's no y anymore. There's just x0 and mu hat because there's no samples, and it's spherically symmetric. It's like rotationally invariant, so it's just characterized by like the distribution of the norm of this thing, the norm of this thing, and their inner product. And we just kind of work hard with chi-square distributions and these quadratic forms to bound the TV distance between the stuff. But it's sort of more painful than insightful, frankly. Was painful. I think it was not, in the end, super insightful. So that's the theorem we get. And as I said, a lot of the work in this paper, I think, was sort of taking this problem we observed in practice, that we have membership inference attacks that seem to be based on kind of non-optimal looking things that seem to use the distribution in kind of limited ways. And we wanted to understand whether that's inherently limiting, or maybe that's not limiting. Maybe what they were doing was actually sort of the optimal thing. We sort of formulated this theoretical model of membership inference that doesn't look that much like practice involving neural networks, but lets us reason about it. And we were able to sort of identify this case where it does look like there's something being kind of left on the table. Like, you should really be using some kind of distribution dependent test statistic, and what people were kind of doing in practice is really suboptimal. And kind of the next thing to do, I think, is to sort of try to understand, what this says in the real world. So, we now have sort of this intuition that, at least in principle, membership inference attacks might require a lot of information about the distribution to carry out. And I think that points to some like interesting questions, either sort of for theory or practice. So certainly on the practical side, I guess the question now is to try using more distribution dependent things. Of course, it's challenging because these are really messy and nasty distributions. And so just because you say you want to do something distribution dependent, it's very hard to extract useful information out of the distribution. It's also possible that the settings in practice that people are looking at just are sufficiently different that maybe you don't get any mileage out of some distribution independent tests or distribution dependent tests, though I'm not sure I believe that. Another direction is to look at the question from a different view. So attacks that people use in practice also don't really exploit much information about the specific training algorithm. They just sort of use the fact that the algorithm is giving a good model. And that's another thing we don't really understand. Like, if you know exactly what the training algorithm is doing, can you get a more meaningful attack? That was sort of not the question we looked at in this paper. We basically only looked at kind of like one specific training algorithm. So of course we kind of knew what it was, but it's not clear what you would do different. And then the last direction, which I think is maybe an interesting kind of theory direction in the near term, is now we know that there's these membership inference attackers that exist, but need lots of knowledge of the distribution. And in the formal model of differential privacy, if you're familiar with it, you want privacy basically against completely omniscient attackers who know the distribution. But in the real world, maybe you don't care about privacy against omniscient attackers. Maybe if you actually have a good reason to believe the attacker doesn't know something, you can exploit that to get better accuracy or lower sample complexity with meaningful privacy. And so our results kind of suggest that there are some settings where an attacker who has limited knowledge of the distribution might be unable to carry out membership inference, or there's very narrow settings where they are unable to carry out membership inference. Maybe this is something you can reason about more generally, that, you have mechanisms that are more accurate than what we know of, and are private against sort of a reasonable class of attackers. So I think this points to that as like a potentially promising direction. So I'll stop there. I hope I can convince you to think about these questions, and I'd love to talk about them. And I will cease. I will.
Awesome. Thank you, John. Any questions?
Lucky if I squeak out an answer. Yeah, Elena?
So. Basically, you're using one.
Where do you want me to?
I guess, I don't know, some. So the mu that you're considering, it's a fixed mu, right?
It's like a fixed algorithm for producing mu. Yeah.
And for this one, you showed by showing.
Yeah.
In and out part distributions, right? So is there a way to say that, like you can, like this is the hardest, or like formally?
Well, I mean, I guess it's sort of the hard, like, that's sort of basically the question of, is our bound optimal? So, I mean, I don't know if the hardest, but like, in some regime of parameters, we get a tight bound. So it's sort of the hardest distribution family, and that, it witnesses the tight lower bound, and any other hard distribution can't give you a much better lower bound. I don't know. I think maybe you want something more specific, like sort of characterizing what the hardest problem is in a more specific way, and I don't.
You have a more something like a better algorithm, like,
Oh, like
yeah,
like an algorithm for, sorry, like a better attack algorithm or a better like private algorithm?
the new. The
Yeah, that's like the estimator.
the tracking.
No, in the sense like, I mean, I think it should be true that. Okay, I guess like, yeah, what is better? So like in terms of sort of getting, like making membership inference not work, this is sort of the right thing to try to do. Like we kind of know that the way you get kind of optimal error for DP in this setting is you design some estimator that sort of tries to add noise of like this shape. But of course, like what we're trying to prove is a lower bound for MIA. So there's definitely other algorithms you could come up with that might like make MIA easy, where you don't need a lot of auxiliary symbols. So I don't know, but I don't know how interesting that would be.
And since we're past one, let's I want to let people take off, but let me also comment that if people really want to meet him,